Sorry for the delay, Butala. Uh, you can see yeah, mechatronics. Butamata mechatronics email address text karan make the chat. Can you text me the mechatronics email address? Hello?
I can't hear.
Again, I had to repeat it. Yeah, I plugged my earphone at the wrong port. Yeah, can you hear now?
Yes, sir.
Yeah, very good. Okay, let me start from the beginning again. Yeah, so this is about the understanding entropy. This is very important, and this has a lot of practical aspects. And if you really can understand this entropy, uh, it is pretty much practical, and that this knowledge may be very important to you. So, my objective of sharing with you about the entropy is not just for a book knowledge but for applications. Okay, applications. So, when it comes to sustainability, we are talking about the sustainable developments and the sustainable energy consumption and all. So, somehow, in all the human activities, if we can have the minimum possible entropy generation, that is considered the best. Zero entropy generation, generally it's not that practical, but if the entropy generation is minimum, that is the best solution approaches when it comes to thermodynamic solutions, when it comes to the even something like when you develop the property developments, let's say when you build the condominiums and all, whatever the entropy considerations are there somehow. Even all applications, even the cooking, household, even designing a bulb, you can see the entropy link, the practical aspects. We are going to sense practically how you can utilize this entropy knowledge. And the other thing is, if you do not know entropy, you do not know thermodynamics. And the other point is, understanding of entropy is very little, even
Sir, ज्ञान है इधर.
yeah, but somehow signal interruption. Hope you're all right. Uh, hope you're all right. Hope you're all right. Yeah. So understanding entropy is so important. This vertical is a surface. Through the surface, this heat is transferring. So heat is transferring to the right side here. At the right side, the heat entering media, the temperature is T. This is not the surface, but this is at the vicinity of the surface, the media temperature T. Because to transfer this heat through this surface, okay? And let's say at a certain period of time, the transfer of heat is delta Q transfer, okay? So when it comes to practical aspects, this transferring of delta Q is to a certain space, and that space at the heat transfer point, the temperature T, and this is the space. So now you can see for this space, heat is transferred delta Q amount at the boundary. Just inside the system, the temperature is T. So what happens is, when this temperature, anyway, at this temperature T, because of this delta Q, there is an increase in entropy, delta S, okay? And you know that delta S is a calculated property, okay? And today we are going to see further practical aspects of this entropy. So delta S is the increase of entropy. Now for this enclosed system, it's something like recognized space, this heat transfer delta Q, and this temperature, the relevant temperature at the space is T, and because of this T, the temperature and the heat transfer delta Q, temperature rise delta S. And as we discussed last week, delta S is greater than or equal to delta Q by T. Okay, this is what we call the Clausius inequality. Okay, so this Clausius inequality is one of the second laws. Okay, second law, one of the aspect is this. In the second law of thermodynamics, this is one of the aspects. The entropy increase is more than delta Q by T when there is a heat transfer. Okay, when there is a heat transfer. Okay, so I have a question. When there is a work transfer, why entropy has no connection? Why only heat transfer has connection? Anyway, later we will look into this entropy concepts further. So you know this very well because in our previous day, we refer the steam table and delta S we calculated, that's a laboratory scale testing. Delta S as equal to delta Q by T. This equality when the process is reversible. Reversible, okay? When the process is reversible. So let me take this, okay? Let me take this to the next slide. Yeah, to the next slide. So delta is greater than or equal to T. Be very relaxed. Eh? Yeah, be very relaxed. So here you can see greater than delta S is greater than delta Q by T, and delta S is equal to delta Q by T. Okay, so two expressions are there. So now I am writing the two expressions representing this. One is equal, other is greater than. Combining both we call greater than equal. Okay, and delta S when it's equal, let me take this first. I have some software issue maybe. Delta S equals delta Q by T. This equality sign is there when this heat transfer process is reversible. When I have issue here. when you have to be patient with this heat transfer of delta Q is reversible. Can you advise me how to this automatically this spell check come when delta Q heat transfer is reversible. So when irreversible, it is greater. Irreversible. Irreversible. Okay. I hope that you can have some practical sense of this. We will try to get practical sense of this. That is very important for both you all and me. The practical aspects of this. Okay. Irreversible. So same delta Q, same T, but when it is reversible, delta S is equal to this. Okay. Which means whenever there is a heat transfer, there is an entropy increase. The minimum entropy increase is delta Q by T when this heat transfer is reversible. Okay, heat transfer is reversible, or the process is reversible. When it is irreversible, delta S is more than delta Q by T. Okay, I hope you got a little bit, not to say a full sense of this, but you have some little bit clue on this. Clue on this. Why delta Q by T consider here? Why delta Q by T consider here? Yeah, as delta S. Okay, as delta S. Why delta Q by T consider here? Okay. So that is the point. So let me duplicate this slide. And I'm going for a case now. Picture here. I'm going to delete this. And just for the memory, I'm putting this picture here aside. Okay. And now I'm considering delta Q for two different temperatures. Okay. Delta Q for two different temperatures. Delta Q for two different or two or three different temperatures. Okay. Delta Q temperature and delta Q by T. Let me delta Q. Now I'm going to take T here. Okay, T. Now watch carefully. Yeah, T delta Q Kelvin. T in Kelvin. T in Kelvin. T in Kelvin, delta Q. And the other one is delta Q by T. Yes, be patient, right? Very patient. Patient. Let's see how this analysis is gone. Put the fonts a bit big. Yes. Okay. Let's say temperature is 27 Celsius, 30 in C, degrees in C, degrees. Yeah, T in Kelvin. So Kelvin, that is 273 plus 27. Okay, 27. That is equal to 300. Okay, and let's say delta Q as kilojoule. Kilojoule let's say 100. Let's say 100. Let's say 1,000. 1,000. Okay. Kilojoule 1,000. Let me take 9. Let me take 9,000. Okay. So delta Q by T means 9,000 by 300. Okay, 9,000 by 300. Yeah, T. The unit is kilojoule per Kelvin. Okay, so this is the unit. So this is the analysis we are doing now. Let's say the next one is I'm taking the same Q. Now you see 9,000. Okay, this one, the temperature I will take as 77. Need to say 77. Let's see 27. 27. Let's say 77. Let's say this is 77. So the T in Kelvin is plus 77 means this is 350. Okay. For same 9,000, this is 9,000 by 350. Okay. What's the value? 9,000 by 350. What's the value? Anyone has a calculator? For the calculator. What's the value of that? Yeah, okay. 9,000 by 350. 350. This is 25.71. 71 kilojoules per Kelvin. Okay. Now I'm going to take further up here, let's say minus 37. Minus 37. Okay. 50. Minus 27, right? Yeah, minus 23. Let's see. I will take minus 23 degrees Celsius. So the temperature is 273 minus 23, because that is plus minus 23 means minus 23. That is 273 minus 23 is 250. Interesting. Okay, 250. Same kilojoule 9000. Delta Q by T is 9000 by 250. Okay. What is this value? 9000 by 250. 250 by 1000 is 4. This is 36. This is 36. Okay. 36. 26 kilojoule per Kelvin. I think good enough. Okay. Now see, same delta Q value. Same delta Q value, but different temperatures. Okay, Kelvin values. You have 250 here, Kelvin. Here 300 Kelvin. Here 350 Kelvin. Okay, and this delta Q by T becomes delta Q by T values become decreasing when the temperature rises. When the temperature rises, the delta Q by T value is decreasing. What is this? Okay. And yes, you can see here. Your delta Q is here. Your T value is here in Celsius first and then in Kelvins, because Celsius we are more familiar, centigrade. And delta Q by T is there at the right side. Okay. And if you think of delta S, okay, if you think of delta S, what happens is, if delta S is delta Q by T, you know what is this? This means reversible. Then your delta S is your delta S value. Then delta S. Then your delta S value here Okay, I'm going to share with you a very important lesson, but this needs some analysis. Okay, delta S value becomes 36 kilojoule per Kelvin. Okay, delta S. For the second case, delta S is 30 kilojoule. For the third case, delta S is 25.71 kilojoule per Kelvin. Okay, so this is the situation. And now I'm going to add one more column to the right. Okay, sorry, one more column to the right. And if irreversible, if irreversible, if irreversible, if irreversible, what you can say is, I am taking the same column. Kutala, you try to understand this. Understand this is very important. That's why I'm doing this evaluation. Delta S, if irreversible, that's what we can say. Delta is greater than the corresponding value. Delta is greater than delta Q by T. Okay. Irreversible, delta S is greater than delta Q by T. Okay. This is something. Let me duplicate the slide. This is the one. I check this text box out and I will use this table here on the right. It's a nice slide. Right side you have the case. Okay. Heat transfer from this surface delta Q and just at the system at the interface between the surface and the space T. Well, the T in degrees finally converts to Kelvin. Delta Q is here, delta Q by T. Remember this T is in Kelvin. Okay, that's the important thing. This Kelvin, this should be in Kelvin. T should be in Kelvin. Okay, the subscript. Let me put it. Okay, so Tk is T plus Tc plus 273 is Tk. Okay, T in Kelvin. T in Kelvin means K. Okay, that is Tk. First, let me complete this because I can share this. Tk is T plus 273. Okay, that decimal number, decimals, but anyway, 273 for the moment. Okay, now use okay. For the same delta Q, when this T becomes increase, your entropy is decrease. Okay. For higher temperatures, for the same heat transfer, you have the lower entropy. You have lower entropy. Okay, higher temperatures, lower entropy, lower temperatures, higher entropy. Okay, I have a question for you, but I hope you can understand this. For power generation, for work done, okay, which temperature is more useful? Higher temperature energy is more useful. Okay, higher temperature energy is more useful. So you can see here, higher temperature energy, this transfer heat is finally comes as energy here. This energizes the system. So this energizes. But anyway, when the temperature is higher, entropy increases less. Temperature higher, entropy increases less. So if I put, let me put quite big value here. So for power generation, generally, let's say your temperature is 300 degrees. Easily, let's say 500, let's say 400 degrees Celsius. Now what happens to T in Kelvin? 273 plus 400. Okay, 400. Let's see, I put this 273. For the convenient, I put here 427. Okay, 427. 273 plus 427. 427. This becomes 400, 600, 700. 700 Kelvin. Okay, same delta Q. So what happens? 9,000 by 700. 9,000 by 700. Okay, 9,000 by 700. This is put the value here. 12.85. See. So your delta S value is 12.85. So delta is somehow greater than 12.85 if it is irreversible. You can see at quite high temperatures, 700 Kelvin to 427 Celsius, entropy increase is only 12.85, the minimum increase. Okay, so we will look into the minimum. But the minimum increase at minus 23 degree negative, entropy increase, the minimum is 36. 36 and 12.8. 36 is almost 3 times. So what is this? How do you find? What is this? You have to inquire this. What is this? What makes this high temperature? Same heat transfer. What makes the entropy less? That's why you have to learn it. Very, very important. If you don't know how to justify, you can calculate the entropy value, but if you can justify, what's the point? Very interesting. Yes, master tip. Master tip. Entropy further understand. Now you have to find the risk. Okay. Now you have to find the risk. Okay. Very interesting. Okay. So this is one of the cases based on the entropy definition. You are noticing. Okay. You are noticing one of the cases. And now I'm going for another case. Okay. And now I'm going for another case, which is really a true case. Okay. Which is really a true mean. This also there. Of course, this is a true case as well. So let me look into another application. Okay. I think let's do in this way. I take a snapshot. Snapshot. Okay. So this is very interesting finding. I copy this. I hope you can see the screen. If you don't see the screen I'm working on, please raise your voice. Yes. It's the same. Okay. It's the same. So now I'm thinking, let's say this is a refrigerator box. Let's say this is a refrigerator box. Refrigerator box. See what can we find. Yes. Yeah, man. Good. So this is the box. So what is outside is insulation. Okay. Yeah, very interesting. Let's say this temperature, if it is equally distributed temperature, this temperature has a value. Even air conditioned space, you will see the same. Okay. Let's say for this refrigerator box, this is more practical situation. Okay, this is more practical situation. So this is the original evaluation. So the next is the, the new consideration. So original, so there's the new consideration. So heat transfer through insulation, refrigerator box, heat transfer through insulation. I'm going to analyze this. Heat transfer through insulation. Heat transfer through insulation. 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 Or for refrigerator or a freezer, let's say. Refrigerator. Okay, refrigerator. So this is the situation now I'm going to consider. Heat transfer through insulation of a refrigerator. This is very interesting. Now see, okay. Now see the situation. Okay. Now you are going to analyze this again. So first case, this is your case. How come? Same heat transfer, different temperatures, your entropy change. You are going to find the answer. What makes this? So what makes this practical sense linking with the entropy? Now for the refrigerator box, again, I'm going to evaluate this and we will see the situation. Okay, we will see the refrigerator box. Very interesting. Okay, this is very interesting. So you have to link. That is what we call understanding thermodynamics, understanding entropies. Let's see. Now the situation is different. Let's say you are controlling the refrigerator temperature. You're controlling, okay? You're controlling refrigerator temperature, okay? And your ambient temperature may be the same, okay? Your ambient temperature may be the same. So what we are doing is, in this analysis, so outside the temperature, so outside temperature, outside, So when you write the symbols, when we do the coding, T outside, let's say 27 degrees. Okay, 27 degrees Celsius. 27 degrees Celsius. And let's say T inside. T inside. So T inside is, now you are going to, how to say, you are going to vary the inside temperature. Okay, you are going to vary the inside temperature. Yeah, because we're adjusting using the thermostat. So what happens to your delta T? T outside minus T inside. ये virus issue. I don't know. T outside minus T inside. Okay. So delta T is T outside minus. So you are going to learn one more thing here. Minus T inside. Okay. T inside. So you are going to learn some more. T outside minus T inside is delta T. Very, very interesting. You should know that for heat transfer, there should be a temperature difference. Okay. T outside minus T inside is T now. T inside is varying. T inside, we call this T in the above figure. Okay. Inside. Okay. T inside is T is varying. Delta T is T outside minus T inside. This is very important. So T now I'm changing here in the table. Let's say I'm going to create the table minus 23. This is the frozen temperature for ice cream is minus 18. Consider is almost 80% of water is frozen at minus 18, minus 23. So minus 22, I think 100% water is frozen in ice cream. So I put here minus 18. Okay, minus 18. It's a good temperature for a refrigerator. Okay, minus 18, consider for the freezer the optimal. And I will put minus 13 here. Okay, minus 13 is the soft serving temperature of ice cream. Yeah, okay, minus 13. And when it comes to the dairy products, okay, 0 to 3, let's say 3, okay, 0 to 3. And let me minimize this text since you're familiar. Change it to 24. Minimize this also. Okay, let it be. Interesting. 3 degree, you know. 3 degree, eh? 3 degree. 3 degree is the optimal for the dairy products. That's why if you have some temperature, the thermal applications about food, yeah, you should know all. Okay, do you know this? And for the beverage, let's say 7 is considered the ideal, the chilled 7 degrees C. Further down, 13 is for the, sorry, 8. Yeah, let's say 8 is for the red wine. 8, red wine. 13 for the white wine, but let's say for the beverage 12. Okay, 8 for the white wine, 12 for the red wine. Yeah. The beverage, let's say one more. Yeah. One more beverage. Let's see, anyway, it's around 12, 13. Yeah. So minus 23 here, minus 18. 18. Here minus 13. Ice cream soft serving. Meat from meat storage is minus 23 is better, eh? Yeah, for the meat and fish. So minus 13 here. 3 for the dairy. Dairy means the liquid milk, right? Liquid milk mainly. 8 for the white wine. 273 plus 8. 8. This is for the red wine and for beverage. 12. Good. So now you have to 273 minus 18. You have to get the figures. You have to get the figures. Now you say because of this temperature, you have the T out. Okay. Now you have delta T value. See delta T now. You have the delta T value. T outside is here. Yeah. So now you have a corresponding delta T values. This is T Kelvin. So T Kelvin, T inside is this T Kelvin. 273 minus 80. This is 255. 255. No idea. I just put it. 273 minus 13 is 260. This is 13. 260. 273 plus 3 is 276. 6. 273 plus 8. Oh, let me not calculate the rest. Eh? 3 is let me not calculate this. It's okay to calculate, but 73 plus 8, 281. Those are very close figures because 3, 8, 12. That's why 73 plus 12, 285. So those are very close figures. But anyway, even a decimal point matter when it comes to entropy. So you have a delta T value and delta Q, okay? You have the delta T and delta Q. And delta Q. So delta T you have 27 minus 23. Your delta T 27 minus 23 is minus minus 23. Sorry, 27. So your delta T becomes Yeah, just put delta T. So your delta T value is 27 minus 23, 20, 24, 50. 50, you can say that is 50 kelvins, delta T. Okay, because T outside is 27 minus 23. So minus 18, you have another value. So 27, 37, 45 minus 45K. Here, so 27 minus 30, 40. 40K. 40K. What's the time? Yeah, we have enough time for the analysis. 40K. 27 minus 3 is 24 Kelvin. So delta T delta T K means Kelvin. Okay. Now 8, 27 minus, yeah, this is 19K. 27, 19. 27 here, 15K. Delta T is 15K. 15K. So when your delta T is different, your Q value is dropping. Okay, your Q value is dropping. So I'm just taking as a case study. This is 8,000. Surely, when your delta T is less, your delta Q is less too. This one, let's say 987 6 6 5 5 4. Again, huh? So this is 9,000 by 250K. Okay, 9,000 by 250K is 36. Here 8,000 by 255K. Interesting, eh? Interesting. 8,000 by 255K. Yeah. Example. Actually, normally the example, this is 45 by 50 times 9,000. Let's see. 45 by 50 times 9,000. 550 times 9,000. 8,100. Okay. That's why it is very close figures. 8,100. This is 50 by 40 times sorry, 40 by 50 times 9,000. 40 by 50 is 0.8. This is 7,200. Get the values. So here 24 by 40. 24 by 50 is almost 4,600. 2,320. For 9,000. 19 by 50 times 9,000. Next one. 3420. 15 by 50 times 9,000. 2,700. So this is very reasonable. Right? Very reasonable. This understanding entropy. Yeah. Now becomes 9,000 by 250. Same. Here 8,100 by 255. 273 minus 18. 255. 273 minus 18. Yeah, 255. Then 273 minus 13. 273 minus 13 is 260. This is 260. Yeah, 260. Yeah, you calculated it. 60. This is 276. 6. This is 4320. I'm very sorry, you have to be very patient because sometimes analysis take time, and it is very important to do this analysis because these are facts there. Yeah, 0, 0. Even you can calculate this. So 3420 by 281. 281. And this is 2700 by 285. 85. We have to get the values. 8100125. 31.76. See how easy it is for a real refrigerator. So when your thermostat setting is at high temperatures, your entropy generation is less. 7200 divided by 260. 7200 divided by 260. That's the value. 27.69. 27.6. Okay. 4320 divided by 276. 4320 divided by 276. 276. 15.65. Very interesting. See, these almost realistic figures. See, 3420 divided by 281. In future, if you don't use the entropy calculations in your system designs, this is 12.17. You are not doing right. Okay, that's why. So here 2700 divided by 2. So this is refrigerator application. This is 9.47. Very interesting. 9.47. So this is delta Q by K. See the values, the radius values 36, 31.76. Next, 27.69. Next, 15.65. For 8 degree, this is 12.17. You see, 3 and 8, 5 degree difference, but your delta S increase. 15 against 12 means there is a 3 kilojoule per Kelvin increase. Decrease means that is 20% decrease. 20% decrease in entropy increase for reversible process. 20% for 5 degree UV. Okay. When it comes to 12, this is 9.47. So now you see in the refrigeration applications, if you set the temperatures not so low but optimal, okay, you are done. Your entropy increase is less. Okay? Your entropy increase is less, and that is the best. This is not about energy saving. Of course, energy is saving. Energy saving is there, but your entropy reduction is impressive. Okay. Even you have irreversibilities, the relative evaluations. You feel good with higher temperature settings. Okay. 9.47. That's why. So when you run with very good PLC controls or with some variable speed drives your cooling systems, your temperature is maintained with less fluctuations and your entropy generation will be less. because increase and decrease. Decrease is the problem, not the temperature increase. So this is a masterpiece. This slide is a masterpiece. So this is another example you are looking at. Okay, I need the answers from you. Okay, these are the examples you're looking at. Real practical examples. How come in a refrigerator when the thermostat setting is at optimal and at higher levels, your entropy generation is less? Very interesting. This is the second master slide. Understand? This is very, very important. It's the same for the same. So when it comes to the next case study, okay, so now better take a snapshot of this or something. So you have to find the answers because this today topic is about entropy further understanding. Okay, so I'm going for another new case. Okay. Another new case. This time your thermostat setting, your temperature is the same. Okay, your temperature is the same. So let's say minus 23. Okay, minus 23 Celsius is the same. Okay. Calculation is quite fast. But now your refrigerator, yeah, now the delta T also same. See, same delta T because outside is 27. Okay, same delta T. But now your delta Q is the issue because now let's say we are thinking of going for better insulations. Okay, we are thinking of going for better insulations. Okay, going for better insulations. What is this? Okay, you are going for better insulations. Okay, going for better insulations. Now what happens is when you have the better insulations, so let me redo it. Sure, I will take the same delta T 50K, same delta T because the inside temperature setting it's at minus 23. Freezer, the freezer for frozen food application. But now what happens is even though the same delta T, your delta Q is different. Let's say this is because of better insulation. Okay, your insulation improving. Okay, let's say this case study for better insulation. This one, this case study is for the better insulation. So I will do the improving insulation. Improving. Insulation. Imperfect. Oh, God, okay. Stop here. insulation. I'm improving. I'm improving. I'm improving insulation. Okay. Improving. Sure. Okay. Insulation improving. Yes. Use this. So when your insulation improves, what happens is your delta Q. Okay, your delta Q delta Q is decreasing. Delta Q is what shall I do? Fine. Okay. Your delta Q is decreasing. So that is the general principle. Okay, that's the general principle. So when your insulation is better, your heat transfer to the refrigerator is less. So this follows. See, better insulation. See, 9,000 reduced to this, but say minus 23. So let's say this is a case. Okay. So now what happens is 9,000 by 250 here. Okay. So this becomes 8,100 divided by 250. Now it's a different calculation. 250. This one becomes 7,200 by 250. 4320 divided by 250. This divided by 250. 7,100 divided by 250. Now see. 8,100 divided by 250. Let's see. 8,100 divided by 250. I should have the time today too. This is 32.4. 32.4. 2.4. That's all. Next is 7,200 divided by 250. You should expect this analysis even in the exams. 20.8. It is very close. It is very close to the increased thermostat setting. 4320 divided by 250, the next case. Divided by 250. 17.28. 17.28. You are never thinking of the importance of insulation because you have no sense, most thermal engineers actually. In Sri Lanka, thermal engineers are very less. Do 700 divided by 250. 10.8. See, now your entropy decrease is so good as thermostat setting increase. But here, your temperature very low. But when you have a better insulation, your entropy is very less. See? So you can see delta is 32.4. So this is the other case study. You have to think this 28.8. You may argue that, of course, when the insulation is better, the energy saving is there, but when it comes to this principle, energy saving means the reduced heat transfer. Reduced heat transfer means reduced entropy. Okay, reduced entropy. So I have generated, how to say, 3 cases, and you see the magical nature of this entropy connection. So later we have to see what makes this link with the practicality, the entropy. Okay, that is very important. So 28, 32.4. Everyone looks very silent. Silence is okay if you really think about this. Yes. So 3 analyses based on the entropy calculations and some practical aspects you have seen. So let me look into these 4 slides. Okay. 4 slides. This one is the same temperature of the refrigerator. You are increasing the, sorry, this is not about the same temperature. This is a case here for delta Q. So let me correct this. I have to say correct. Let me explain from here. Okay, this is the one. You can see this temperature T inside this system or the chamber or the space, enclosed space. You are increasing T, so your outside maybe the outside whatever for the increase of T, but you are maintaining same heat transfer. You can see the delta Q by T. Your entropy increases. This. So higher the temperature, entropy decreases. So this is one of the case you have to think. How come when the temperature higher, when the heat transfer towards the high temperature? Of course, it is high to low, but this low temperature, when this T has a higher value, entropy increases less. So this is one case. This is the same here. Instead of this Just the square box, I took the refrigerator space and went into this case. Now your thermostat setting you are changing. Yes, thermostat setting you are changing. So that is the approach. So this is the one. You can see the minus 23 for frozen, minus 18 optimal frozen, minus 13 is also considered serving condition. 3 dairy, 8 for white wine, and 12 for the beverage, including red wine. So here, TK, now you can see when the delta T change, delta Q change, delta Q by TK change, delta S. If reversible, this is how S. If delta S is delta Q by T means reversible, this is how delta S. If irreversible, this is the case. So very interesting. You can see when the thermostat setting goes high, the delta Q value becomes reducing, and finally your delta S entropy increase within the system is decreased. So then this is the case. Go with the beta insulations. So you can see same thermostat setting, insulation level increase, insulation quality increase, your heat transfer to inside reduce, and your entropy increase reduce. It is dramatical reduction. So that is the 3 cases now. You have to look into these 3 cases, and after looking into this, you have to understand what, okay, what this entropy means, some practical aspects. Okay, some practical aspects of entropy. Okay. So I'm going to take from the dictionary what entropy means. Okay, yeah. So beyond this, actually I'm going to discuss this in another session because it is almost reaching the 3:30, and anyway when we discuss this way, it is a bit tired maybe. You're thinking, you're focusing this. So entropy, a thermodynamics quantity representing the unavailability of a system's thermal energy for conversion into work. Unavailability of a system's thermal energy for conversion into work. Okay, so this is one of the explanation. Unavailability of a system's thermal energy for conversion into mechanical work. Okay, so the entropy increase means your energy, unavailability of energy for mechanical work. Okay, that is what entropy increase. So you see here, in this case, when the temperature is high, higher temperature of energy availability means, of course, high temperature energy, you have a high chances to convert to mechanical. Example, at 427, your high temperature, 427 Celsius, high temperature gas, you can expand and you can do some work. So at 427, unavailability of energy for mechanical work is less. You have to follow. At higher temperatures, when the heat transfer it is high, so high temperature here, unavailability of energy in this heat of delta Q for mechanical work, maybe to drive an engine or piston, is less unavailability. minus 23, very low temperature. This so at so this delta Q transfer at minus 23, very low temperature heat, you cannot convert to work. That's why your unavailability of energy is very high. Unavailability of energy for mechanical work is very high when the temperature is very low. If this 427 happen to be 1000 Celsius, your unavailability of energy for mechanical work is very, very less because your energy at delta Q, high potential to use as to get the work done. But I got the point? Yeah, got the point. So this is the important thing here. So anyway, yeah. Says the entropy always increases with time. So let me take this out for this moment. Take this out. So I need you to focus on this. Okay, so this is one of the definitions you are focusing on. So I'm going to save this, and today I'm going to send this to you right now, so you can analyze this. Okay, Vika? Yeah, you can analyze this and you can see how well matching this. So this is the entropy in physics. Okay, entropy meaning in physics. You know, in physics means this is the pure definition. Okay, entropy meaning in physics. I have issues here. Entropy. I'm very sorry. I don't know how to resolve this. In physics. So you know physics is very important. Engineering also appears a discipline because of physics. Yeah. Physics is the key for engineering. Yes. For engineering also, this is the definition. So, very good. So this is the PowerPoint we have developed, we have discussed this. I hope you understand this very well. And this understanding is very important. If you know the entropy definition, the practical aspects, you know how to develop the very good systems. That's why this needs some general understanding of this kind of, not to say concepts, but some truly realistic knowledge with some philosophical aspects. Yeah. So minimizing entropy, if you receive the energy for a piston to get the work done, that receiving of heat, same like delta Q there, you know, heat should be at higher temperature. That's why diesel engines, high entropy. I think diesel engines, the temperatures are higher than the petrol engine. Energy saving is better in the sense the fuel consumption is more somehow. So you can see high pressure engines are quite okay than low pressure engines. High temperature engines are better. So anyway, they all are related. Then the better lubricant, the lubricant functions. That's why lubrication one way important to control the frictions and all. Friction is something generates unnecessary heat with no use. We call this irreversibility. Actually, irreversibility is one thing. The unavailability of heat for mechanical work, for conversion into mechanical work. That's why. So friction will be one of the culprits, one of the reasons for the entropy increase. There are many. So let's discuss. Let's discuss this. We have to continue this dialogue. for another day because I'm going something like I need you to understand this very well. So let me go to the mailbox and Zoom. So, sorry, classroom, Thermodynamics. So I will try to launch. Try. Let me browse it. Launch. Browse. Tutorials. Entropy further understanding. Stability. Good. About to pause this. Entropy. Further understanding. I hope you all will get this. Hope you all will get this and go through this. Go through this. As well, I will upload the recordings in the web. So I hope today good discussion, good explanation for you. So let me stop the class now. Before that, any question, any practical questions for you, whatever? Yeah, open for discussion. Anything? From my side, I have one point. I have one thing to mention. The workshop practicals, we should not get late for the workshop practicals. So at least within the coming weeks, within this month, we have to finish it. So somehow you have to sacrifice for that. So Hasita and Umesh may be the two representatives. Yeah, please arrange the timing. Yeah, and let me know as well. So we will do it. Yeah, that is very important. So simple practical anyway, CA part is important. Utala, okay? Are you okay? So let me stop the class. Hope you got something useful. So we will continue learning. That's all from my side today. So see you next time. Good luck to you all. Let me end the class session. Okay, Putana. Bye then. Bye.
Goodbye, sir.
Bye, sir. Bye. Thank you.
Thank you, sir.
Okay, Putana. Bye.